In linear algebra, there is a central theme to write a matrix in a better form by changing coordinates. Of course, what better means depends on the matrix itself, and also on the potential applications. For example, by changing coordinates, some matrices take diagonal form. This is the easiest class of matrices to work with. Among these, the ones that can be diagonalized through unitary matrices are especially important. In what follows, the space will always be finite-dimensional. The inner product is linear in the second variable and conjugate linear in the first variable. This is consistent with physicist notation. It is also convenient for several reasons that will become clear later. The class of operators to be considered here is called self-adjoint. It is one that can be moved from one side of the inner product to the other side, without any change, or, under any orthogonal basis. Its matrix representation is conjugate symmetric. For example, the standard basis in Cn consists of n unit vectors. In general, there are many other orthonormal bases. For every fixed basis, an operator has a corresponding matrix representation. Keep in mind that the same operator have many matrix representations. The spectral theorem says that for a self-adjoint operator A, there are always n eigenvectors and n real eigenvalues. The eigenvectors form an orthonormal basis of the n-dimensional space. The proof of this theorem will be left to the end. We will explore what the theorem means and put it in several equivalent forms that are easy to generalize to infinite dimensions. Let's first look at the eigenvectors of A. Each eigenvector of A is a column vector. If they are put into a matrix U, then the multiplication of U by A from left is equal to U times a diagonal matrix D. The matrix D consists of the eigenvalues, lambda 1, lambda 2, up to lambda n. Therefore, AU equals UD. Because the columns of U form an orthonormal basis, the matrix U is unitary. In other words, the product of U and its adjoint is equal to the identity operator. Now the operator A is unitarily equivalent to D. Another way to say that is the diagram commutes. From the above discussion, we see that A is equal to U du star. U is a row of column vectors. These columns are U1, U2, U3, up to Un. They all have norm 1 and are mutually orthogonal. On the other hand, the adjoint of U is a column of row vectors. For example, U1 star is the conjugate transpose of U1. Similarly, U2 star is the conjugate transpose of U2, and so on. With all these notations in mind, and use the fact that both U and the adjoint of U can be written as block matrices, the equation A equals U du star takes the following form. This form of the spectral theorem contains products of column vectors and row vectors. These are called tensor products. For example, U1 times U1 star gives an n by n matrix. This is a rank 1 operator. It means that the range of this operator is one-dimensional, because it sends any vector W to the one-dimensional space spanned by U1. So it maps W to some constant times U1. This constant or coefficient is precisely given by the inner product of U1 and W. We now introduce Dirac's notation. Using this notation, every column vector is called a ket vector, and its conjugate transpose is called a bra vector. For two vectors, U and V, in the n-dimensional complex vector space, their inner product is the product of the bra vector of U, and the ket vector of V. Therefore, the product of bra and ket is a complex number. On the other hand, the ket, bra product of U and V is different. It is the rank 1 operator, whose range is the one-dimensional space spanned by U. We have seen that ket, bra, is a rank 1 operator. A special case is when taking a unit vector, say U, and form a rank 1 operator. This is an orthogonal projection. In general, an operator is an orthogonal projection if it is idempotent and self-adjoint. The term orthogonal means that the projection of a vector on the range of P and the projection on the range of 1 minus p are orthogonal. If the space is three-dimensional, and we use the standard basis, then the projection onto the span of E1 has the ket bra of E1. Similarly, you can find the projection onto the two-dimensional subspace spanned by E1 and E2. In general, the sum of two projections is not a projection. It is true when the product of such two projections is 0. Here is another example in the three-dimensional space. Take a vector u equals 1, 2, 0. It is not a unit vector. To get the projection onto the span of u, the vector must be normalized. This is why the constant square root of 5 appears. Then the projection onto the span of u is the ket bra of u0. We are now ready to state another form of the spectral theorem for self-adjoint operators. Remember, the eigenvectors of A are mutually orthogonal, and these vectors form an orthonormal basis in the space Cn. First, using the ket bra notation, the operator A is the weighted sum of mutually orthogonal projections. The eigenvalues are not necessarily distinct. Some of the eigenvalues may appear multiple times, so we regroup the eigenvectors for the same eigenvalues. For example, if lambda 1 equals lambda 2, and the rest of the eigenvalues are all distinct, then we factor out lambda 1, and get lambda 1 times the sum of two projections. In this case, lambda 1 has multiplicity 2. In summary, if we use distinct eigenvalues, lambda 1, up to lambda m, then A is a weighted sum of orthogonal projections. The rank of each projection is not necessarily equal to 1. The rank is the same as the multiplicity of corresponding eigenvalue, and the sum of the ranks is equal to the dimension of the whole space. For the projections, they are mutually orthogonal, each one is self-adjoint, and the sum is the identity operator. This is called a resolution of the identity. Here is the conclusion from the above discussion. Every self-adjoint operator corresponds to a unique resolution of identity of the space Cn, and the operator is a weighted sum of the orthogonal projections. The simplest example is when the operator itself is diagonal. This 4x4 diagonal matrix has 4 eigenvalues, but 3 distinct eigenvalues. Lambda 1 equals 2, with multiplicity 1, lambda 2 equals 3, with multiplicity 2, and lambda 3 equals 5, with multiplicity 1. Now we break up A into 3 parts. Each part is the projection onto the corresponding eigenspace. We can use Dirac's notation to write down these 3 projections. Under the standard basis, P1 is a projection onto the one-dimensional subspace, spanned by E1. P2 is a rank 2 projection. It is a projection onto the two-dimensional subspace, spanned by E1 and E2. P3 is also rank 1. Its range is the one-dimensional subspace, spanned by E4. Finally, let's sketch the proof of the spectral theorem. We choose an arbitrary orthonormal basis for the whole space Cn. Then every operator has a matrix representation. From the fundamental theorem of algebra, every complex matrix has at least one eigenvalue. The first step here is to show that if a matrix is self-adjoint, then its eigenvalues must be real numbers. Suppose U is a normalized eigenvector corresponding to lambda. On both sides, take inner product with U. Since the inner product is linear in the second variable, lambda can be factored out. It now becomes lambda times a norm squared of U, which is just lambda. Because U has norm 1, we have lambda written as the inner product of U and AU. The operator A is self-adjoint. It means that A can be moved to the other side of the inner product. The inner product is conjugate linear in the first variable. When flipping the inner product, there is a complex conjugation. And finally, S is the conjugate of lambda. The last line shows that lambda must be a real number, as it is equal to its complex conjugate. We have one normalized eigenvector for the eigenvalue lambda. Let K be the span of U, and look at its orthogonal complement. This is the set of all vectors that are orthogonal to U. In fact, when the operator is self-adjoint, it leaves this orthogonal complement invariant. In other words, it sends any vector back into the same space. The reason is very simple. Take U and V as above. We want to verify that AV is also orthogonal to U. So we look at the inner product of AV and U. It should be 0. Since A is self-adjoint, it can be moved to the right side of the inner product, but U is an eigenvector, so AU is equal to lambda U. Factor out lambda, then the inner product of V and U is 0, by assumption. Let's put things together, but relabel some variables. First, we get an eigenvalue lambda 1, and a unit eigenvector U1. The whole space breaks up into a direct sum of K1, and its orthogonal complement L1. The restriction of the operator to L1 is also self-adjoint. Therefore, the restricted operator has an eigenvalue lambda 2, and a unit eigenvector U2. Let K2 be the span of U2. L1 also breaks up into a direct sum. It is the direct sum of K2, and the complement of K2 and L1. Let's call this orthogonal complement L2. Therefore, the whole space is the direct sum of K1, K2, and L2. Repeat the same argument, we end up with a direct sum of n components K1, K2, up to Kn. The last orthogonal complement Ln is 0. Each K is the span of a unit eigenvector. These eigenvectors form an orthonormal basis for the whole space. In particular, they are mutually orthogonal by construction. This is the end of the proof.